we can just start then. We've got just over 2 hours to run this workshop. It's the first educational workshop that has been hosted by ECCA here in Europe. David, who I'll come to in a moment, has run a number in the US as part of the NCCA. But from an ECCA perspective, we hope it will be the first of a number that will run over the coming years. Now, one thing that I would ask you from the first slide is we want to make it as interactive as possible. There's nothing worse than sitting for 2 hours listening to grumpy old men talk about things that maybe are not of interest to you. So we wanted to be interactive. So the agenda is quite ambitious. So we've got just over the 2 hours. I'll introduce it perhaps a bit more formally in a moment. David will talk a bit about cause and effect and defect analysis. I'll spend a little bit of time on substrates, whether it be steel or aluminium. And then David will go into more detail on the type of paint defects and the causes of those before I wrap it up towards the end. So, in terms of who we are, this is me, Terry Goodwin. I'm Sustainability Director for ECCA here in Europe. Before I took up that role, I retired from Tata Steel, where I was Marketing Director. As part of my CV, I was President of ECCA about 10 years ago. My involvement with coil coating is 28 years and growing. I've worked in R&D, I've worked in market development, and I'm a chemist by training. So when I wrote that, I thought 28 years is not a bad sentence, involvement for an industry, but I suddenly decided or discovered that in fact I was a junior. In this relationship, I'm the junior partner. David is Technical Director of NCCA. It's great to have him here for this event. He presented to the Congress this morning, very interesting presentation on colour. Before he took up that role, he was the Director of R&D for AXO, so he complements my steel background with the paint side. And as you can see, he's had a number of positions within the NCCA and various committees within the US where he's used his expertise to further the industry forward. 45 years is a real achievement, I think, something that he should be congratulated on. For those of you, and I'm sure there are some in this audience who've been in the industry maybe less than a year, you've only got 44 years to go. So welcome, David. Hopefully we've not done this together before, but perhaps it'll be an example of the special relationship that exists between the UK and the US. The background to today is that the ECCA board, which met yesterday as part of its ongoing program of meetings, has long believed that helping people learn and understand about the industry is very important, how to give people access to the knowledge and information that will help them do their jobs better. The ECCA Academy was the first step in that, and it's available, and Yvonne showed some statistics yesterday which showed that over the 10 years that's been in existence, it's continued to grow. There are a significant number of people who've enrolled for that scheme. And never too proud to copy. As I said, David has run a number of these in the US over the past 2 to 3 years. It looked like a great idea. He's willingly given up his time and a lot of the content for today. So hopefully you will enjoy it. Right, so why do we pick surface defects? Well, the European coil coating industry is, I'm sure you'd say, globally competitive. Yeah? We saw yesterday with Eglantine the amount of exports that go out of Europe to far-off markets. Believe it or not, you're part of an industry that employs over 5,000 people and turns over just about 5 billion euros every year. There's a mix between steel and aluminium. That looks quite heavily weighted towards steel on a tonnage basis, but of course, if you do it by area, the aluminium contribution is significantly more. And there's a lot of paint, yeah? 200,000 tons of paint per year that's consumed by these coil coaters to satisfy a market which, if you saw the statistics yesterday, has doubled in size over the past 20 years. The problem for us, of course, is if we have a 1% rejection rate, and we'll try and find out what that rejection rate is later, that's worth roughly 55 million euros to the industry a year, yeah? At times when manufacturing, steel, aluminium, struggles for profitability. That's a big chunk. So the cost of quality for this industry is quite significant, and hopefully by the time we've finished, you might be able to do something better to reduce that, or whatever number the cost of quality is. If I look ahead, I'm sure you'd all recognize this schematic about the coil coating line, but it's fair to say we face a number of challenges. We have to reduce the amount of energy that we use. There's a lot of work going on at the moment about the new BREF document. We have to eliminate hazardous substances. Chromate is the one that everybody comes to mind. More environmentally friendly products. Anita was talking about bio coatings yesterday. And we have to increase the performance or the aesthetics of the product. So there's a lot of challenges that the industry has. And they will all serve to make the manufacturing process far more complicated. Because the parameters will need to change. We may have to go to new curing technologies. We may have to go to new finishes. One thing's for certain, the challenge will not help the quality problem that we have. So in terms of the objectives for today, we'll hopefully explain to you about the different types of defect that you can see on painted metal, whether it be steel or aluminium. We'll try and identify what the defect is. We'll explain where that defect's come from and maybe how you can prevent it. That, of course, is if any of you admit to ever seen a painted defect. There was one question I was asked you, have you ever seen a defect? I think most of you would, in public, admit not to have seen a defect. It's one of these things that people aren't prepared to admit to. But anyway, in terms of coverage, we can't go into in-service performance or problems in fabrication. This is all about the manufacturing defects on the coil coating lines. Maybe those topics would be something for a subsequent workshop. So hopefully we'll help you understand the cost of quality and how to reduce it, and maybe prepare you to help develop the industry, because the challenges are certainly there, and for us to remain globally competitive, we need to improve. If we look at coil coating, one of the things that you may not realize, if you've been like David, submersed in an industry for 45 years, you may not benchmark yourself across other industries. And these are a couple of slides that David had put together for the American session, and I think they're really interesting in terms of what they're saying to us. Across the top, you have a number of different factors: dwell time, temperature of curing in the oven, and a number of different industries. So if you look at coil, the area coated per minute, maybe 250 square meters. The only other industry that comes close to that is packaging. Spends 15 seconds in the oven. Auto refinish are there for 5 minutes. It's a really interesting slide in terms of putting this industry alongside others. I think it's fair to say that no other industry coats as much product, as fast, with such a short cure time, for products that maybe have to last a long time. The product always gets fabricated and goes into a wide range of applications. So this industry is special, We may not realize that when we sit in the office on a day-to-day basis. But if you look at a benchmark exercise like David's put together, you see that this industry has some very unique characteristics, which hopefully we can exploit for market advantage, but certainly makes the quality challenge even more important. If you then take the market view, then we produce product that looks really nice on buildings. We produce product that looks really nice in the house. And we saw yesterday the statistics to show that appliance had grown substantially over the past year. We make all sorts of very attractive and functional products. But they've all got some things in common. All your customers, wherever they come from, like a high-quality defect-free surface, but it's got to be in the right color. It's got to be able to be fabricated, and it's got to last as long as it's going to need. And 40-year guarantees are pretty commonplace for the construction market. So the quality challenge then that we face is a combination of the process. Go back to Henry Ford, all these cars that have to be black. I'm sure our manufacturing colleagues would like to produce one size of coil in one color, day in, day out. I see that in every company. The product technologists would like to build in as much sophistication as they possibly could to produce those elegant products that will meet market requirements. But the market itself is moving, yeah? What was commonplace 10 years ago as an application maybe isn't today. So these are really quite conflicting priorities in terms of what the product needs to be, how it's made, and how it finally performs. So quality is a very complicated situation, complicated by the fact that it's subject to all these forces, and typically you've got different people inside the organization championing those different agendas. We're almost perfect, but we're going to use 1% as an industry average, made up of a number of sources of defect, substrates, perhaps the minor contributor, application problems, and paint, and then a collection of others. 1% on its own sounds really quite interesting, but perhaps not significant. But if you quantify that up, yeah, it's equivalent to nearly 9 million square meters of painted steel every year that perhaps we chuck in the bin. Just over 1.5 million square meters of aluminium. So it's dangerous just to think about the 1%. I'm sure your quality managers will say that's not acceptable. When you take it as an industry-wide problem, it's a big issue. And it certainly is going to cost the industry 55 million euros or even more by the time you get into rework and quality functions and so forth. So it's an expensive business, poor quality. You'll see through the rest of the afternoon some examples of what poor quality looks like. But hopefully you'll take away some information that will help you understand this. Okay, so that's an introduction. Hopefully I've set the scene, tried to explain to you who we are, why we're here, and what we're going to do. I'll hand over to David now, who will take us through the next section of the presentation.
So first, let me tell you what 45 years in the industry does for you. If you think it means that I know everything, you're really wrong. Frankly, I learn as much from the audience as I give to the audience, because we're dealing with extremely complicated issues when you're talking about applying a thin layer of paint at fast line speeds, curing it quickly, and then you have to fabricate it. And if it's a building product, it needs to last for a very long time. So 45 years means I don't really know everything. In fact, sometimes I feel like I don't know very much. 45 years does mean that I've seen a lot of presidents, going back to John Kennedy and Richard Nixon and the Bushes and the Obamas and the current one, if that's what he's going to be called as a president. But I'll tell you one thing that 45 years does mean. That means I've probably have made every mistake that you can make in this business. And I've made 2 doozies that I'll never forget, but they've taught me so much about the importance of getting down to the root cause of something and trying to understand cause and effect. Now, for those of you with advanced degrees, you know this is complicated stuff, and you can only spend so much time really trying to understand the real cause. You've got a job to do, you've got a customer to satisfy. Nonetheless, the thing I try to inspire people to do is try to get to that root cause, try to understand the cause and effect. But at some point, you got to draw the line and say, let's move on. I think I've got this problem solved. I'm not quite sure why. I don't think it's going to occur again. So I'll give you a couple of examples of my doozies. But first, we're going to talk about cause and effect, because I think it's just very important that you've got to get this education. This is why we're here, right? We're here to learn something. And the education has to lead somewhere. It has to lead to an understanding. And it's really, understanding is more than what. I mean, we know what happens. You've got a poor pencil hardness. You have a poor T-bend. But the real question is, why is it happening? And I challenge you, by the way, don't leave that kind of concept here in this conference room regarding paint. Take it home when you're trying to solve some problems too. I've stopped trying to explain to people what exactly takes place in a can of paint. To the best of my understanding, I can tell you that it's awfully complex, but there's a lot of elegant chemistry, but there are never any simple questions, no simple answers. And I always found this interesting that, we love these Apple products, but these guys worked hard to make things simple. And that's what we all really do. We work really hard to make things simple. When that coil is delivered to your customer, they shouldn't have to appreciate one bit how much difficulty went into the chemistry of the paint, the metallurgy of the steel, pre-treatments, cleaning, application, cure response, and all of the QC that goes into it. So when we're talking about our business, we're trying to generate a deeper understanding of what's happening with the problems that we're dealing with. And of course, the best way to know that you've got a handle on a problem is if you can turn it on or turn it off. If you think you understand a problem, can you do something that turns that problem on and do one more thing that turns that problem off? It's the best way to understand that. And we're not going to solve all the problems today. There's just too many interesting things that happen with coatings. But first, let's try a little bit of this. We've all talked about correlation. In my talk this morning about color, I was showing some pretty darn good correlation between Delta E Hunter and Delta E 2000. But then there's causality, which is, why does this happen? So I've got a slide here that shows that if you eat more chocolate, you get smarter. I mean, the correlation is indisputable, but you can't really believe, right? You can't really believe that that's the case. Although, being in Belgium for the first time in my life, I'm stunned by how many chocolate shops there are. So maybe this is the smartest area. You may find this interesting. There's lots of tests that measure correlation. You've heard of gauge R&Rs that you've done, Pearson coefficients, maybe Spearman rank for some weathering tests. There's not a single statistical test that tells you that you've got your hands around the causal relationship. And that's why we have meetings like this. We can debate sometimes whether you think you're right and you know why you're right. So here's a good example. A kid's in an airplane, and he's obviously quite perturbed because of the turbulence. And look what he says. I wish they didn't turn on that seatbelt sign so much. Every time it does, it gets bumpy. Well, he's made the correct observation. He's simply drawn the wrong conclusion. So we all have to be careful of that. You just have to challenge yourself. And one of the best ways to do that is talk to somebody with experience. In this room, we had, 20 years was about the mean? For the younger people, never be shy about talking to someone else. Hey, did you ever see this happen before? And I do the same thing, by the way, with 45 years of experience. Hey, did you ever see this happen before? In my case, it's always a quest to try to see if I can put one more piece of the puzzle together to see if I truly understand what's happening. Okay, Terry, I'm going to turn it over to you.
Right, so on a number of the charts, we've got some smart people in the audience, which is a challenge for us. There are some long-standing experts, but the next bit is about the substrate. I'll cover both aluminium and steel. Two very, very different metals, but they have a number of things in common. The first thing, of course, is that the upstream of the coil coating line is quite a complicated manufacturing process. This is the steel one. You've got to make the steel, you've got to cast it, you've got to hot roll it, you've got to cold roll it. In most cases, it's got to be galvanized, and then you ultimately get to coil coating. Yeah? The bottom is a schematic of a galvanizing line, which in itself looks a lot more complicated than a coil coating line. So no doubt those of you who run or take upstream supply, you think maybe these guys have got it easy, but they haven't. They've got quite complicated processes to run. Same with aluminium. This is the aluminium process flow. They extract bauxite, make alumina, smelting, similar to steel making. It's cast, hot rolled, through to rolling. The only piece that they haven't got in their process that's in the steel side is the galvanizing process, because aluminium is corrosion resistant, whereas steel obviously will rust unless you protect it. So two very complicated upstream processes. But in some ways, they've got no excuse, because if you think about the markets the big steel companies supply or the aluminium companies supply, they supply markets which in themselves are probably more demanding than coil coating. Yeah? For steel, automotive is a major market, and people would recognize Volvo as being a company that makes safe cars out of high-strength steel. And people would recognize Audi as being a leader in aluminium sheet steel for the bodywork. The thing in common, of course, is that the steel or the aluminium for these vehicles has to have what you would call a showroom finish. When you go to buy your new car, the first thing you look at is the bodywork. So these upstream processes are quite capable of providing the surface quality that the cold coating lines need. And on packaging, steel cans, aluminium cans, I think almost impossible to tell the difference except if you stick a magnet next to the steel ones. But here, these process routes are providing something that the consumer is satisfied with, whether it's printed or not. And that steel is incredibly thin, far thinner than goes into a standard cold coating line. So upstream of your cold coating line, whether you're part of an integrated supply chain or you buy material from an external source, you should be getting product from a supply chain that's capable. So I'm going to talk very quickly in terms of trying to keep up with time about substrate defects, which are roughly 15% of that 1%. They can come from a number of places. I've tried to explain to you very quickly the upstream processes. If the rolling process, whether it be aluminium or steel, is not under control, you're going to get mechanical properties. Tension leveling is where those upstream will try to flatten and smooth the metal. Poor control there will lead to problems. Hot dip galvanizing itself for the steel part of the business has its own problems. You'd be surprised how much damage is caused on incoming coils because of poor handling or poor storage. Despite some companies having what they think is the right quality processes, there are some examples in here where maybe they haven't got it quite right. So if we take wavy edge, then you can see that right-hand side, not perfectly straight, buckling up and down, can be a problem for the applicator rolls. That's going to be coming from the rolling and the annealing and tension leveling upstream for your product. You take coil set. This is where your mechanical properties are not quite right. The coil is effectively frozen. You look at aluminium, you get some rolled in defects, a lot of friction marks. On galvanizing, on steel, you might think maybe you can hide those roll marks by dipping it in the zinc. Sometimes that works, sometimes it doesn't. Waviness is an interesting one. That's a very informative picture of how that aluminium surface, that mirror surface, is not as it should be. If you had that ahead of your coil line, you'd be thinking whether you want to coat it or not. As it says, that's all from the leveling process in the upstream. Bad edge is another one. For some market sectors, they'll accept a mill edge finish. For many, particularly the more higher quality ones, you've got to edge trim. That's a poor steel edge. But it applies to aluminium as well. You can see physically the metals are very different in terms of their properties, density, and all the rest of it. But in terms of the quality problems that they experience, there are great similarities between both substrates. Holes. How many of you have seen coils that have arrived at your cold coating line with holes in them? No. I've never come across one like this, but it's an astonishing example of how maybe the upstream or the galvanizing line has not managed that coil in the right way. How it gets through quality release procedures amazes me. You can get dents, physical damage to the coils. Again, if you were supplying automotive, this would have been rejected at the end of the galvanizing line. How it's got through to the cold coating line is of interest. But it's not only a steel problem. There are some dents there in aluminium, which again have come from that rolling process. Some coils are welded, which are problematic to the coater units on the coil coating lines. Some are scratched. If you go through either process route, the number of rolls in the through process is quite considerable. A galvanizing line, will have 10, 20 maybe, depending on its configuration. And scratches usually come off a roll If you go back to Dave's point about cause and effect, trying to track back through that upstream process where and how that coil got scratched, it can be a real challenge for the through process team. See scratches on aluminium as well. So these next ones are more around steel. This is galvanized slag, a residue from the galvanizing process. You'll have examples of dross coming through on the surface, little flecks of inorganic material off the galvanizing line. As I said, most of the galvanizing lines that supply coil lines are probably automotive capable, at least to GP finish standards. So their dross control procedures should be really very good. But they're not, and you get to see material there. And you can see some clearer spots on that. Not only does that compromise the surface finish that you're looking for, it can also interfere with the corrosion protection that you're looking for by disrupting the zinc layer. This is an extreme case. We all talked about, or most of you voted for surface cleanliness. This is delamination of that galvanized coating, which is more often than not caused by poor cleaning on the galv line. So the whole point about a coil-coated product is getting that intersurface, those intersurface properties correct. Otherwise, your product will not look good and probably not perform as well as you want it to. We're now starting to get into kind of the more storage, handling kind of problems. This is a stain which has come from water somewhere in the process. Water ingress, particularly on steel, is an issue. If you decide to store your galvanized coils in a shed that leaks, you're going to get white rust. Yeah. So there's a whole range of different surface defects there that you can see on your coil coating lines. They're manifestations of problems in that upstream process, whether at the rolling stage, which are more related to mechanical properties, to the rolling stage, where you begin to get scratches or surface contamination, particularly from the galvanizing process. Then you get into physical areas where the transfer between the upstream supply chain and the coil coating line is not perfect. The coils get knocked when they're on cranes. They get put in sheds that leak. All of this goes towards complicating the quality problems that the coil coating line has, because as David will explain in a moment, there's enough issues around how you get the paint on properly and making sure that paint looks the right way without having to bother with these kind of defects. So I'm sure when you go back to your organizations, particularly those of you from the coil coating businesses, maybe you want to just go back and talk to your upstream and say, well, you know, what are you doing to improve the quality into my line? Yeah. There's always this concept of the internal supplier customer, which has its own issues. But the first step in trying to solve some of this is making sure your substrate is right. Because as I said, David will take over in a moment and talk about all the difficulties that you coil coaters have in putting the paint on, because they need to have the right paint from the paint companies applied to the right pre-treated surface over the right metallic substrate. So I think that might be the last slide. Right, David, I've provided you with perfect substrate.
Okay.
There's absolutely no problems, no scratches, no nothing on this substrate. So all you've got to do now is paint it properly for us.
All right. Okay, application and paint issues. We don't call them paint problems, we call them paint issues. When Terry put this slide up, it was pretty apparent that of the 1%, which is admittedly a small number, a fat part of it is paint and application issues. And you know, why is that? Well, I'm using this river as an example that you've got two complex processes that are coming together, and that doesn't make it a simple process. That makes it more complex yet. So when you're talking about application problems, we are often referring to the issues that are occurring in the coater pan, having to do with either the pickup roll speed, the applicator roll speed, nip pressure, kiss pressure. I mean, you know, you've heard all these terms before. The durometer of the applicator. Of course, the quality of the metal. If you've got a bad edge and it tears up the roll, now you're going to have some blistering problems. From a coating standpoint, we are thinking in terms of we can control the viscosity and the rheology in an effort to affect things like edge bead. But I have to say, I've been at this for 45 years. This aspect of fluid dynamics is underappreciated. It's underappreciated because it's so complex that it's difficult to understand. I don't pretend to understand it. I'll give you a glimpse of it, though, so that you can see what it's like. So when it comes to rheology, just to remind people that we can take the viscosity using a Zond cup or a Ford cup or something, but rheology is really what it's all about. That's the study of viscosity, but it's also the study of viscosity under various forms of shear. That's way more important on a coil line than you think. And shear is nothing more than these two plates sliding past each other. And what ends up happening is viscosity rheology is the resistance to flow. And it's unimportant to understand things like shear rate, but we'll talk about it in a little Excel sheet in just a second. Typically, our coil coaters are not Newtonian. Newtonian means it doesn't matter what the shear rate is, it's the same viscosity. Water is a good example of a Newtonian fluid. Our paints tend to get thinner as you put shear on them. So when you're running it through a pump, when you're running it through a mill, when you're stirring it up in the coater pan with the applicator roll, you're applying shear and the viscosity is dropping. So I've got a good example of what shear thinning is like. If we can play the video in the back. Hello? Oh, is it playing? So this is just a good example of a solid metal ball suspended in a highly viscous solution. And they're going to put this thing on a vibration plate, which is going to vibrate the flask only a little bit. But when that happens, it reduces the viscosity enough, and now you see the ball falling through it. This is what we're talking about when we say shear thinning. Okay, so I don't know if this is a typical arrangement in Europe. This is a very typical arrangement in the US. You've got a coater pan with a pickup roll. You have the applicator roll here. I'm showing the backup roll going here. You have the web coming through it. The applicator wipes the paint on. And then on the back side of the strip, you have another pan with a pickup roll and an applicator roll, and the strip then goes into the oven. Is that typical here? Or do you typically run 3-roll setups on this side? Two choices, 2-roll or 3-roll. Say something. 2-roll, okay. 3-roll. Yeah, or 4, okay. Yeah, I think we do this in the US for a very important reason. 82% of everything that's done in the US is building products. Appliance is very small. Transportation is very small. So we're constantly painting over galvanized and galvalume, rough surfaces, and this becomes a very simple process. These guys are the ones that really understand fluid dynamics. I attended one of their conferences one time. I didn't learn a thing because it's just way beyond me. But what I grew up calling this reverse roll coating, because the applicator is going in this direction and the web is going in this direction. These guys call it forward roll coating. And I had a long talk with them, and their point was this process right here, where the rubber roll puts the paint onto the web, that's a wiping process, that's a low shear process. All the shear is between the pickup roll and the applicator roll. So, and it's really the differential in speed that's occurring along with the pressure and the durometer of the applicator roll that makes a difference. So when you shear the paint, that creates certain problems, but it's also creating good flow because it brings the viscosity down. And these are probably difficult pictures to see. We do have a few panels up here, but you can control the appearance a lot by managing the differential speed between the pickup roll and the applicator roll, and then also managing the line speed itself. So here we're looking at these stripes. This looks to be a textured paint. Probably what's happened is part of the texture has gotten in between the pickup roll and the applicator, and it's left a little bit of a void. That's a very difficult problem to occur when you're running textured coatings. You probably already know that, and there's no simple solution to that. So all I've done, let me just stand back here. You're certainly welcome to this spreadsheet, but there's a formula that is going to, well, first of all, the inputs are very simple. Dry film thickness, volume solids, which then gives you the wet film that has to flow onto the web. You've got line speed. Sorry, I'm using feet per minute. So, or as they say in the US, we're converting to the metric system inch by inch. So we got line speed at 300 feet a minute. The applicator roll speed's 400 feet a minute. Then this is the pickup roll speed. So the question is, okay, if you have to run that pickup roll speed very fast, you're not going to have an awful lot of shear. But if you can run that roll speed very slow, you're going to have a great deal of shear. Let me give you an example. That 45,000 reciprocal seconds of shear, that's probably the greatest amount of shear that you can apply to any fluid. Paint guns are operating in this range. The high-speed turbo bells that you might have heard of are operating in this range. So we actually do develop a lot of shear by creating a differential between the pickup roll speed and the applicator roll speed. And in the next slide, I'll show you why that's so important. Okay, so we're showing here a schematic of the pickup roll, and you're forming a region here which is called the film split region. Obviously, some of the paint goes on the applicator, some of the paint stays on the pickup roll, but where this region splits, and there's a formula that's used to run the spreadsheet, this is where the ribbing occurs, okay? The ribbing is not occurring between the applicator and the web. The ribbing is occurring between where the film splits between the pickup roll and the applicator roll. If you run the applicator roll as slow as you can, what you'll do is you'll create a larger number of smaller ribs. If you can't afford to run the pickup roll slowly because you can't pick up the paint, then you have less shear and you'll have a larger number of fatter ribs. And this is what's creating the ropey flow that you see at times. Here's a little video. Now this happens to be a cellulosic material, so you can really see in slow motion what the ribs look like. By the way, this wire wound bar, this is not a bad proxy for duplicating the kind of flow pattern that you see on a coil line. It doesn't have anything to do with generating shear. It has to do with the fact that the paint's only oozing out of the gaps. So that's why a wire wound bar still works as well as it does. So here's an example of ropey flow. What would I do? Well, I would probably try to slow. You have to maintain the applicator roll in conjunction with the line speed. But I'd say the first thing is try to slow down the pickup roll. And when you slow down the pickup roll, that creates more shear. When you create more shear, you form a larger number of smaller ribs, and you overcome that. Guess what? If you slow down the pickup roll too much, you can't get enough paint put onto the web, and you may run into starvation problems. So a good practice that many people try to do when they're trying to about coatings on a coating line, you should get into the practice, however it's best to do it on your line, to try to understand how slowly you can run the pickup roll, because that's going to give you the best results all around. Now you can't run it so slowly that it starves out. but it's worth considering. Just don't follow the old habits. Don't take this coating and think that throwing some solvent in it is going to overcome ropey flow, because that may not be the solution. So here's some flow stripes. Again, we've got this panel up here. We've got many of these panels up here. This is a textured product, and I don't have a lot of experience with texture. It's not a very popular finish in the U.S. I don't know how you can overcome this easily. Does anyone here want to volunteer a solution and help the coil coating industry globally and conquer the world? Or not? Okay. Anyway, those are difficult problems. Many cases, I could imagine you get something trapped in the nip of the applicator and the pickup roll. Again, stripy finish. This could be caused by any number of things. Again, this happens to look like a textured coating. Here, you're seeing these stripes sort of going this way. Maybe these are washer marks. There's a good case of trying to do a root cause analysis. It may actually be pretreatment stains that are given this appearance. Again, more examples of poor leveling. We might as well talk about it at this point. You can improve the flow of a coating by reducing that coating surface tension. There's all kinds of ways to reduce that coating surface tension. But the problem we have on a coil line is, if you form this ropiness, what is it, maybe 2 seconds before the coil goes into the oven, and 5 seconds later you've lost maybe half of the solvent, so now your viscosity is so high that you almost don't have a prayer of smoothing that out. So we'll talk about surface tension in just a bit. But I would say that from my own personal experience, increasing the shear rate solves a lot of these issues. And the only way you can really increase the shear rate on a coil line is to run the pickup roll more slowly. And again, I'll discuss a little bit more of this in detail when I tell you about my perfectly bad experiment. Well, there's starvation. Okay, so you've now slowed down the pickup roll because Cocuzzi said to do that, and look what happened. I got into trouble. You just can't get enough paint there, and we've got. I don't think this shows up so well here. This panel in real life is amazing. It looks like puffy clouds on a piece of metal, where you've got thin spots and thicker spots, but it really just looks cloudy, like you're looking at cumulus clouds. That's a result of the pickup roll not running fast enough. You just can't put enough paint onto the applicator. You can't put enough paint from the applicator onto the strip. It's a cool effect, but you really don't want to see it too much. And the only way to put more paint on the strip is to increase the pickup roll speed, which decreases the shear, which increases the ropiness, or increase the nip, increase the gap between the pickup roll and the applicator, which decreases the shear, which increases the ropiness. So we're in a really tough business when you get right down to it. And I know that many of you folks, according to the poll, 20 years you've been on this line, and a lot of this you just take for granted. So do I. I put that chart together that Terry was showing you because when I talk to my friends that are working with coatings for concrete or automotive OEM coatings, and they hear that we've got 15 seconds to bake a coating, which is going to be fabricated after the fact and last a hell of a lot longer than car paint, they can't believe that we're able to do it. But we are. We can get some odd issues on the back side of the strip, and I think once we cover this, Yvonne, would be a good time for a coffee break. When you press that applicator roll onto the web, and in many cases you're pressing it right up against the backup roll, and that's okay. If you've got wavy edge, this has been taped just for protection. When you have a wavy edge like this, you can overcome a lot of that problem because you're pushing so hard. But if you've got the backside, so this is the backside of this panel. On the backside, if you here, there's only so much tension that you can push up, right? There's only so much that you can push against that web. So it just creates gaps on the backside. Now, this may not be rejections. I mean, maybe not too many people are concerned about this. But if you've got someone that can see this backside on the inside of their building, this is a big problem. And there's no way around it. You got to talk to Terry to fix his metal. Right, Terry? There's just all kinds of problems that you can get. This is a sample from the U.S. We've got streaks this way. We've got paint globs this way. We've got other gaps that have formed. This is all in the same sample that was sent to me. And again, I think part of it is it's hard to get a lot of shear on the backside coating, and it's hard to overcome the problems by putting more kiss pressure onto the backside. So I mean, these are clearly some metal issues that just can't go away. You mentioned surface contamination is maybe one of your biggest problems. One of our biggest problems is mill finish. So we actually have these nooks and crannies, sort of like an English muffin, and the coater's attitude is your paint has to fill that in. Sometimes you can do it and sometimes you can't. So here's a good example of paint that is simply not filling in the gap as well as it could. Now, in this particular case, it's the backside. The backside is put on here at about 10 microns, so fairly thin film, and it may have a micron or two of primer. Here's a good example of water that wasn't squeegeed off properly on the backside, but it was squeegeed off properly on the front side. So now the backer is trying to flow over water, so you can see where the primer is. You know, some of the paint is there, but it's just a mess, right? So this is a case where you'd want to go backwards and look for where the squeegee rolls are not doing their job. And I love this example. This is flying paint. You've got a red that's being applied here. Probably the pickup roll or the applicator roll are running too fast, and the paint's misting off and is falling all the way onto the backside pickup roll, transferred to the applicator roll, then to create this little finger paint effect. It's shocking how many things can go wrong on the backside of the coating when you're always focused on the front side. That's what makes it fun. Here's a beautiful one. This is now the front side, and those aren't punch outs. Those are two little drops of white paint that have fallen into this coating, and because they must have fairly low surface tension, they've pushed that green paint out of the way and to form a perfect circle. See, only coil coating people could look at defects like this and consider it art, right? Wow, you know, rubber-coated applicator rolls take a beating, especially when you're running some holes in galvanized. So you form a nick, and usually the coaters can pick this up pretty quickly. But you can imagine this metal is coming off at 100 meters a minute, 200 meters a minute, and you're trying to assess very quickly what the defect is and then how to solve it. And usually the first thing you have to do is stop the line, which means you're going to burn something up in the oven. So it's a tough job that we have when we have a continuous operation. More holes, no need to talk about that so much. Roller damage. And we'll cover just a few more things, Yvonne. Always remember this. If this is a typical folding table, maybe it's this wide, and if we put a cross-section of pre-painted metal on it like this, the majority of that metal is cold rolled steel. And we are taking and putting on a thin layer. In the case of steel, we're putting on a thin layer of zinc, or maybe zinc aluminum, or maybe zinc aluminum magnesium. And then we're putting on a relatively thin layer of organic coating. So the other thing to remember is we take a boring piece of steel and we really turn it into a material that's going to give you fabrication properties and longevity like no other coated product that anyone manufactures. Okay, 1.5 years was the length of time it took to understand a problem. The length of time it took to fix the problem was about 1 day. Here's what happened. We made a modification to a formulation, and it worked on 51 out of 52 coil lines. But it didn't work on the 52nd coil line. And of course, we knew we had made a change, and now something went wrong, but only at that coil line. So to get out of trouble, we simply changed back to the earlier formulation. Everything was just fine. But our customer, thankfully, was the kind of person that said, I want to know why it worked at a number of other coaters that he was buying from. Why does it only not work here? Well, you know, we went through all the typical problem solving that you do. Long story short, what we determined was this coil coater decided to save some money, and instead of using softened water, they started using in their primer quench well water with 600 ppm hardness. Now, I would not have necessarily thought that that would create a problem with our top coat, but it did. And then we were actually able to duplicate in the lab by taking distilled water and hitting 600 ppm hardness with magnesium and calcium, and we duplicated the effect. The most gratifying experience of that was we made a presentation to this particular coil coater, and of course we were prepared to get killed because we were going to say it was really their problem. The plant manager, as soon as he heard the argument about hard water, he ran out of the meeting. And what we had learned was he had gone back and he turned the switch to start running deionized water on the quench. So it was like, okay, this guy probably knew all along that you shouldn't be using well water to quench a strip, but it doesn't seem like anything goes wrong. But it did take us a long time. But here's a good case. Why does the hard water quench create problems? That's the point where I drew the line and I said, I just don't think I have the time and the resources to understand the chemistry that's going on. I can guess, but to go further, I can't. So at some point, we all have to say, that's enough of the investigation. Let's get back to making money. So when you go into a coil line, what I'm showing here in this picture is you've got this huge piece of steel, which is a heat sink, and you're going into a really hot oven. And we've got a thin coating, but the thin coating is going to heat up because of this air, but the substrate's going to keep it cool. And what ends up happening is you end up with all kinds of issues, but primarily you're going to have problems with blistering if you don't get the chemistry right. So here I'm just showing that you've got hot air, cool metal, cool paint, and with time, the metal starts heating up. And if you've got solvent trapped in the coating, and if the coating begins to cure on the top, but you still have some solvent that has to evaporate, you start forming at least the possibility of a bubble. Now, you know, this may sound crazy, but I can't tell you how many months of my life I've been on coil lines trying to overcome things like this, whether you call it solvent popping or solvent boiling or blisters. Basically, it's all the same thing. You've got to somehow get the majority of that solvent out before the film becomes cured enough that when the solvent begins to blow out, it won't form this volcano. From a chemistry standpoint, we do that by modifying the crosslinker that we're using, the acid catalyst. We might block the acid catalyst. There's a host of solvents that we would choose. So these problems, thankfully, are not common, because what happens in a thin film like this, maybe it's 15 microns, maybe it's 20 microns, this is not a usual event. What does happen, though, and let me just get right to it, are edge blisters. Now, I don't know that you have a problem like this here in Europe, but a typical coil bake in the US is about 15 seconds. So these blisters are forming right on the edge, and they're forming on the edge because there's a bead that's developed. And we've probably debated for 15 or 20 years why that bead is there in the first place. And I've got multiple pictures of this. And the bead is always the same. There's always an area that's relatively flat and no blisters, and then you form blisters. Over here, the same thing. You have an area that's not got blisters, and then blisters. There's always this tiny little gap. And a cross-section of that would look something like this, where here, first of all, you see that a piece of metal, of course, does not have a perfectly flat edge, so that may be one of the explanations. But typically, about 1 to 2 millimeters from the edge is where you have the height of that blister or that bead. So that bead can be about 1.5 or 2 times as thick as the paint in the center of the strip. So instead of 15 or 18, maybe it's 25 microns or 30 microns. Now that's a challenge to try to prevent solvent popping on something that thick. And more and more pictures here. We've had this problem in the US. It's been minimized through paint formulation by very carefully finding the right catalyst combination and solvent combination. However, so we're away from blisters. We can talk about orange peel. Orange peel is just one of those flow issues. It's the kind of ropiness that gets transferred into what looks like orange peel, an orange peel surface. I wanted to skip ahead because there's some things that I definitely want to take my time explaining while not running over in time, because there's a red card there waiting for me. So
most people who drink wine have seen the weird drops.
This is
that
part of the
form
answer.
around the side of the glass. Traditionally, they're called tears or legs of wine. But what most people don't realize is that if you watch patiently, these drops are actually moving around. They're falling, forming, and refalling over and over and over again. So the obvious question is, what the hell is going on here? First, you have to understand one thing about surface tension. And a neat way to see this is by pouring water onto the surface of a plate and then grinding pepper flakes onto the water's surface. Now, the idea of surface tension is that fluids always pull on other fluids nearby, but the strength of that pull depends on the fluid. So some fluids have high surface tension, others have low surface tension. In our case, we just have water, so the surface tension is the same everywhere. Each pepper flake feels the pull of surface tension, but feels it equally in every direction, so nothing moves. But if we dip a stick in laundry detergent, which has a lower surface tension than water, and then touch the stick to the center of the plate, the pepper runs away. And it runs away because of the difference in surface tension. The higher surface tension water on the edge of the plate pulls harder than the detergent in the center.
So I mentioned earlier that
what does this
if you're a
have to do
paint
with
guy, you've got
Well,
all kinds of
wine
additives to
is
lower
made
the
up
surface
of
tension,
mostly water and
silicones,
alcohol.
fluorocarbons,
And
any
alcohol,
number of things.
like laundry detergent,
And
has a lower
we do
surface
spend an
tension
awful
than water.
lot of time on surface tension
The
because
other
you
thing
read in the
about
books
most
that it helps
alcohols is
flow. And one of the arguments for edge beading was that you put paint on a strip, and just like those tears of wine, surface tension wants to push that paint out to the edge. The problem with that argument is By the way, now we're getting into causal relationships, okay? We know that edge beading occurs. Now we're debating why does it happen. Wine viscosity is whatever it is, but paint's about 200 times the viscosity of wine. So it's hard for me to imagine that paint is going to get pushed there. So for the longest time, I felt like this edge bead, which you have an issue with too here, this edge bead is actually deposited on the edge of the strip. And I've asked myself, why is that? Well, this is my argument, and by the way, when you get into trying to talk about why you think there is this causal relationship, this is where the debate, the academic debate occurs, and that's what makes things fun. You've got a rubber-coated applicator roll, and I'm trying to show here that now you're looking at that strip coming right at you. So this would be the backup roll, this would be the strip, and here's the rubber-coated roll. And of course, it's flexing over this piece of metal. This is not drawn to scale by any means. And eventually, it can get to the point where it contacts the backup roll. And so this is my own perfect line run. We were trying to produce a perfectly smooth, high-gloss white coating. I mean, it just had to look like a mirror. It was going to go on very smooth aluminum, so there was a lot of requirements. And I was a younger guy then, and I thought I knew a number of things. I knew I wanted to make that flow as Newtonian as possible. I didn't want it to have ribs that formed that wouldn't flow out, so I wanted it Newtonian. I also knew that I wanted to keep the surface tension as low as possible, so that in case there was ever any kind of a chance for it to move to the edge, it would happen. So high gloss coating, high gloss white coating, and I didn't do it by design, but it was a perfectly bad experiment, but that doesn't mean you can't learn a lot from a perfectly bad experiment. It took me about a decade to actually realize why it was all bad. Like I said, I've made every mistake, so when you've been in the business 45 years, you've got plenty of time to learn what went wrong. So here's what happened. Remember I showed you this curve where you get some shear thinning, and that's what paint does. And I showed you this curve here where if you could run at very low applicator speeds, you have high shear. Pickup roll speeds, you have high shear, but down here you have very low shear. Well, my coating was very Newtonian. And what we found out was we were having a difficult time building film because we couldn't pick the paint up out of the pan. So what's the first thing you do? You increase the applicator roll speed. Well, actually what we saw first was starvation, so we knew we were about as slow as we could go. So we had to increase the pickup roll speed. Now all of a sudden, and I mean immediately, we saw a ropey flow. By the way, our competition was on the coater upstairs, and their flow was just perfect. So it was very disappointing. So we thought, we'll push the applicator harder against the web. That's got to do something, because I thought that's where a lot of shear took place. I learned later that's just a wiping action. That didn't help at all. We kept on putting on more and more roll pressure, and eventually we painted the backup roll. And this is where it was like an epiphany. The moment we painted the backup roll, we had terrible edge blisters. So in my opinion, that bead is put on the edge as a result of either painting the backup roll and some of the paint is coming back on the edge, or even if you don't paint the backup roll, you can just visualize this, right? Sorry, but there is paint in that on the roll right there. So I think what's happening is, just because of probably some kind of viscoelastic effect, that paint ends up being snapped back onto the roll to form the bead. If you're looking for a simple explanation for how you get rid of that edge bead, I don't have it. What we did was to contend with the thickness of that bead by making sure that thick paint doesn't blister. Surface tension, however, surface tension differences, however, is the explanation for why you get craters and fisheyes. In that particular case, even though it's probably not a big problem on a coil line, that's where you really need to have a surface tension modifier to try to eliminate the differential that occurs. And we've got, you know, plenty of examples of holes in paint. Dirt in paint, well, this is just something that is a natural event. The paint companies do a pretty good job cleaning up dirt, but there's dirt on coil lines, and probably you're running the paint through a filter bag anyway. But this happens occasionally. It happens more likely, by the way, if you do not have a coater room that's using filtered air. So you always want to watch out for kind of fugitive particles dropping in. And we have plenty of pictures of paint and dirt streaks. In this particular case, the most lines probably are catenary lines here. And if you don't have the catenary right, then it just scrapes against the bottom of the oven, and you get a failure like that. Another example of the strip hitting something. I mean, I don't know what it is. There's things in the oven that it's going to bump into. Okay, Terry, I think it's up to you, or over to you.
Right. Okay. So we're almost there. This is what you've all sat through for the past hour and a half. This is what you've all participated in. Hopefully you found it worthwhile. As I said earlier, we hope it's the first in a series of similar events that ECCA here in Europe will organise. We tried to explain to you what the different types of defects are, why you get to see them on a coil coating line. We've covered, as you've seen, from wavy edge through to blisters, paint starvation, paint splashes. For an industry that's quite sophisticated, if you remember that slide I showed about the fact that we paint more surface area faster, quicker than anybody else. The number of quality issues that we have in the industry is quite diverse, which means for those people that spend their time having to solve the problems, they need to have the right approach to cause and effect. Hopefully you can all go back and tell your colleagues about the value of the session and that it's helped you understand how maybe you can reduce the cost of quality. If you think about the 55 million euros, what that might mean for your own company. If you can think about the millions of square meters that this industry wastes every year because of these defects. But you also need to reflect the fact that we consistently try to develop the industry. It's a very good part of the metals industry to be in. It's a market that's continued to grow over a long period of time. And particularly for the people that are new to the industry, the challenge is to pick up the baton from people like myself and David, who've spent a long career associated with the industry. So with that, I think I'm very close to the end. I think this might be the last slide. So I hope you've enjoyed it. Please give us the feedback. There are no more polls, and a safe trip home. Thank you very much.